Hello and welcome to this video on isotopes and average atomic mass. Just want to take a moment to say, look, I know it's hard sometimes, and if you're feeling down, just think like a proton and stay positive. You really should understand why that's really funny. If you don't, you might want to look up protons. Okay, what are we doing today? In this video, the point is I want you to be able to describe an isotope by its mass number and use the rounded average atomic mass of an element to calculate the number of neutrons in its most common isotope. That may not make any sense right now. Hopefully it will by the time we are done with this video. Okay, what the heck is an isotope? Let me give you an example. So hydrogen is element number 1. It is the simplest element and lightest element. It also happens to be the most common element in the universe. And most of the hydrogen that we ever come across is in the form of what you see right here. It has one proton and one electron, right? Just one proton, one electron, no neutrons. Its mass number is 1. And that is the hydrogen that you would find in the H's of H2O, right? So regular, plain old water is 2 of these hydrogens and 1 oxygen. But there is something called heavy water. Weird, huh? There's something called heavy water. How can water get heavier than it normally is? It's not much heavier, but it's a little bit heavier when it's made with a form of hydrogen called this, deuterium, right? So deuterium, here's the name. Deuterium is a proton and a neutron plus an electron. So it actually has twice the mass of regular hydrogen. And that kind of hydrogen goes into heavy water. So it says D for deuterium to make sure we know that it's not the same as H for hydrogen. It is a kind of hydrogen. It's an isotope of hydrogen. Isotope. And heavy water, water where the hydrogens are actually deuterium atoms, is something that is very involved in nuclear weapons and nuclear power. It is not by itself radioactive, but it can lead to the production of extremely dangerous materials when it is used in a nuclear reactor. And that's why, one of the reasons why it's so interesting and important to know about. Okay, so let's quickly define what an isotope is. Isotopes are atoms of the same element with different numbers of neutrons in the nucleus. So we just saw hydrogen, 2 different kinds of hydrogen, right? Regular hydrogen, no neutrons in the nucleus. Deuterium, which is in heavy water, that's 1 neutron in the nucleus. There's actually tritium, which is 2 neutrons in the nucleus, and that is quite radioactive, but also extremely rare. Isotopes have the same atomic number, right? So they're the same element, they have the same atomic number and the same number of protons. But because they have different numbers of neutrons, they have different mass numbers. And then there are 2 ways of writing isotopes, generally speaking. We either say the element name and then the mass number with a little dash in between, or we put the mass number above and to the left of the symbol for the element. Okay, here's an example of how you would write these things. So again, here are our 3 kinds of hydrogen that I showed you already. This is the most common kind. Hydrogen with just a proton in the middle, right? No neutrons. So you write here for mass number. This is its atomic number. Mass number of 1, and then you also write hydrogen 1. Deuterium, which is in heavy water, is a proton and a neutron, right? 1 of each. That gives its mass number 2. So we put the 2 there, or we say hydrogen dash 2. And then tritium, as I mentioned, is a 3rd and even more rare form, where there are 2 neutrons in the nucleus plus that proton, so it gives it a mass number of 3, and we would write it as hydrogen 3. Okay, and so what is average atomic mass? Average atomic mass is a little different, but very related to mass number. And average atomic mass is a number that you actually see on the periodic table of elements. So if you looked at the periodic table of elements, for oxygen, you would see this. You would see the atomic number of 8, right? And those are the number of protons, and then you would see this, and it's not a round number. Well, this is supposed to be protons and neutrons, right? This right here is supposed to be, if it's mass, it should be protons and neutrons, and how can you have 0.999 of something, 0.999 of a proton or neutron. Well, you can't, right? That doesn't really happen. The reason that we have these decimal numbers is because some isotopes are more common in nature than others. But we don't readily distinguish them, so we actually average out, we get a weighted average of all of the isotopes found in nature. So you're not going to find any single oxygen atom with that 15.999 mass in there. What you're going to do is find a whole lot with 16, and then a smaller number with, say, 15 or 14 or something like that. And we get this number by calculating a weighted average of all of those different isotopes. What is a weighted average? This is a concept that students struggle with, but it is also a really important concept because this is how your grades are calculated. So weighted average is an important thing to know. A weighted average is where it's the average of a set of numbers where each number is given a specific weight, right? In a sense, you could think of it as an importance. So let's say you were taking an English class, an LA class, and this is what the teacher decided. The teacher decided that your quizzes in the class are going to be worth 20%. 20%. That your exam was going to be worth 35%, and that your term paper was going to be worth 45%. Right? And so these are things you often would hear at the beginning of a class. This is what the different weighting categories are, but did you ever think about what this is really going to do to your grade? So let's say you did pretty darn well on the exam. You got a 90 on the exam, right? And you did okay on the quizzes. You got an 82. But you did not do great on the term paper. You got a 76. Well, here's how your grades are going to be weighted out. This 82 is going to be multiplied by 0.2. 0.2 and 20% are the same thing. Two different ways of writing the same thing. And so that leads to 16.4. That's then the exam gets multiplied by 0.35 for 35%. And the term paper gets multiplied by 0.45 for 45%. And so these are the numbers that come out when you multiply them, and then what you do is you add them all together. That's why I have a plus here. You add them all together, and then you can see, well, that's why you ended up with an 82.1 as your final grade. So the exam and the term paper counted for more. In fact, the term paper counted for the most of this. So different things matter different amounts in your classes. And that's kind of what we're doing when it comes to average atomic mass. So, for example, this is carbon. Carbon, again, is the atom that is most commonly found in living things. Carbon-based molecules is what most of us are made out of. And the most common flavor, if you will, the most popular flavor of carbon is carbon-12. And so that's this one right here. Carbon-12, that's 6 protons and 6 neutrons. And almost all of the carbon on the planet is carbon-12. So 98.9% of all the carbon that you find is carbon-12. So the chances are, if you scooped up 100 carbon atoms, 99 of them would be carbon-12. And then you have this other isotope, carbon-13. So that's 6 protons and 7 neutrons. And that's 1.1% of the carbon that you might find out there. So chances are, if you scoop up 100 carbon atoms, you have 1 carbon-13 atom in there. And then there's this less common form, carbon-14. Carbon-14. Carbon-14 has 1 more neutron than carbon-13. So it has a mass number of 14. It's pretty rare. It's less than 0.1% of all carbon. So that's less than 1 in 1,000 carbon atoms. But it's still out there and it still matters. So what is the average atomic mass of carbon? Well, we could do it simply by saying, taking each one of these numbers and multiplying them by the weight, if you will. So 12 is the mass number of the most common one times 0.989 or 98.9%. Then we take 13, multiply it by 0.011 for the carbon-13, and we take 14 and we multiply it by 0.001, right? And then we can find out what these numbers are using a calculator, which I have right here. So 12 times 0.989 is 11.868. 11.868. 13 times 0.011 is 0.143. And 14 times 0.001 is 0.014, or 0.014. Add them all up together. You get 12.025. 12.025. That is the average atomic mass of carbon, and that's the number that you would see if you look for mass on the periodic table of elements, because you don't readily distinguish. It is possible, but not easy, to readily distinguish which kind of carbon you have. So if you wanted to know the mass, this is the easiest number to use, and there are specific reasons for doing that. We'll get to those later. Who cares, right? Why is this necessary? Well, there's a lot of difference in some of these isotopes, and the carbon example that I gave you is interesting because we actually are able to take use of carbon-14's rarity and the fact that we know how long it takes for it to break down to do really cool things like date objects, figure out how old certain objects are. So if you have something that had a lot of carbon in it, like a piece of wood, you can look at the ratio, how much carbon-14 there is to carbon-12, because carbon-14 decays. It is a half-life of 5,700 years, which means after 5,700 years, half of the original carbon-14 would be gone. The carbon-12 does not decay, so you can compare the ratios and calculate fairly accurately how old something is, and that's super useful for, say, archaeologists. So here's Mesa Verde, famous national park in southwestern Colorado, where you can see these massive structures built by the ancestral Pueblans. And one of the reasons that we know so much about them is that we were able to take things like a piece of wood that was left there and date it and figure out just how old it is. And so carbon isotopes are really useful for that. Okay, and so what do we do with this average atomic mass number? Well, because one isotope is generally much more common than the others, you can determine the mass number for the most common isotope by rounding the average atomic mass. So you just round the average atomic mass until you get the nearest whole number. You can figure out what is the mass number for the most common isotope and then use that to figure out neutrons and protons and such. For example, what is the mass number of the most common isotope of fluorine? So this is what you might see, say, for fluorine on the periodic table, the mass, and what information do we have from it? So let's see. Above it is this number 9, and sometimes on the periodic table you see it above, sometimes you see it below, but they're in order, so it's not hard to do. And that is our atomic number, right? So I can put that 9 right here, and I know what my atomic number is, and the atomic number is the same as the number of protons, right? So I put the 9 right there as well. Atomic mass. Now, this is the average atomic mass right here. And to make things simple, because I have to figure out the number of neutrons, I'm going to put it right here and say, this is the rounded number. I'm sorry, I'm going to put this right here and get the rounded number of 19. And then to find the number of neutrons, I'm going to subtract these two numbers and get 10, right? So the most common isotope of fluorine should have a mass number of 19, which would give it 10 neutrons. And then for electrons, since these are all neutral, doesn't say anything about an ion, which we'll get to later, we're just going to say same number as the number of protons, 9. Okay, and then one last example of the importance of isotopes is nuclear power. How do we figure stuff like this out? So how does a nuclear reactor work? Well, what you need to do is you need to get a lot of a specific isotope of uranium, uranium-235, which is this kind right here, which has 3 fewer neutrons in its nucleus than the most common kind, which is uranium-238, and happens to be pretty radioactive. So in order to make it useful for most nuclear power plants or bombs, what we do is we enrich it. So we take a centrifuge and separate by mass the two different kinds of uranium and end up with a sample that is a lot more U-235, which is really good for nuclear reactions, especially fission. So hopefully that is going to bring the idea of isotopes together with nuclear power and atomic bombs for you. And you've learned what isotopes are and how to use average atomic mass. I will see you in the next video.